Hi. Today we're going to talk about rational functions. So we're not really going to learn anything really new, but rational functions are a little bit harder to deal with than some of the functions we've dealt with before. So they're a good test on whether using derivatives will help us graph rational functions. And then we'll do one Maxmin problem that involves a rational function. So here's the example that I'm using. Now, the first thing you're going to have to do differently with rational functions is we learned a little bit earlier in the chapter on limits, rational functions tend to have asymptotes, both vertical asymptotes and horizontal or end behavior asymptotes. So the first thing I'm going to do is check for vertical asymptotes. And if you remember, a vertical asymptote is when the function value goes up to infinity or down to negative infinity. And the only thing that makes that is if you have a value of x that when you put it into the denominator you get 0, and the numerator you get something other than 0. So what you're doing is dividing a number by something really, really small, which makes it go really large or really, really small. So I think we can see pretty here that from here that x equals 4 and x equals negative 4 both make the denominator 0 and not the numerator 0. So both of those are going to be vertical asymptotes. So x equals 4 and x equals negative 4. We're going to have vertical asymptotes. So we might as well put those right in there and we can label them. Now, end behavior asymptotes we get by taking the limit as x approaches infinity and the limit as x approaches negative infinity. And I think you might remember that when the highest power of x in the numerator is the same as the highest power of x in the denominator, when you take the limit of this as x approaches infinity, you're just going to get the coefficients, 2 over 1. We basically can ignore the 8 and the 16 for really large and really small values of x. So that means when we take the limit of this, as x approaches infinity or negative infinity, we get 2. So the function value basically is leveling off at 2. We have a horizontal asymptote, y equals 2, and it happens at both ends of the graph. So we've taken care of that. Now, one thing the vertical asymptotes do is they break this problem up into sections. In this case, 1, 2, 3 sections. So between the vertical asymptotes is going to be a section, and then to the left and to the right. So now we can go into what derivatives can do to help us. So we're going to take the first derivative, and we can't really simplify it, so we've got to do the quotient rule. So we go low d high minus high d low all over low squared. And we hope we can do a little bit of simplification. Well, in the numerator, if we distribute that through, we get 4x cubed minus 64x, and then we get minus 4x cubed, and then plus 16x. So the 4x cubes cancel, and negative 64x plus 16x is negative 48x. So we get negative 48x, and in the denominator we still have this x squared minus 16 squared. Now what do? We set the derivative equal to 0 or undefined, just like in all the other cases. And we do find that at x equals 4 and negative 4, the derivative is undefined because we'd have 0 in the denominator. But we have to keep in mind that yes, we want to call those points on our number line because they are going to be important, and it's where derivatives could change from positive to negative. But we have to also realize that they're not going to be local maxes and mins because there's asymptotes. There's no function value there. But we still do want to put them on our number line. So what I do, I just make little asymptote marks there just to remind me that those aren't going to be local maxes or mins. Now, where is the derivative going to be 0? I think x equals 0 is that spot. And then I just plug numbers in to see whether the derivative is positive or negative in those areas. The nice thing to know is the denominator is always positive because it's squared. So if I pick a negative value of x, I'm going to get a positive. And if I take a positive value of x, I'm going to get a negative value. So you can see the only place that the derivative changes signs is right here at 0. So the function is going to go from increasing to decreasing, where in this area it's increasing, and in this section of the graph it's decreasing. So we can see from here that the only local maximum is at 0. And if I put 0 into here, I get 1/2. So at 0, 1/2, we have a local maximum. And then I could say there's no local minimums. Then we're ready to go to the second derivative. We get to do the quotient rule again. So we start out x squared minus 16 squared times the derivative of the numerator minus high, so that means plus 48x, d low. Well, to take the derivative of the bottom, we have to do the chain rule. So we go 2 times x squared minus 16 to the first power times 2x, all over the denominator squared. So we get x squared minus 16 to the 4th power. You can see why these are a little bit messier than the functions we've dealt with before. What can we factor out of the numerator? Well, I've got an x squared minus 16 and an x squared minus 16. The lowest factor is to the first power, so I can factor out an x squared minus 16 to the first power, and there's a 48 here and a 48 here. I'm going to factor out a negative 48. Now, what does that leave us with? It leaves us with 1 x squared minus 16 here, and then minus 4x squared. All over this denominator, x squared minus 16 to the 4th. Well, I hope I can cancel something. I see x squared minus 16 there. I can cancel one of those. And here I end up with negative 3x squared minus 16. And I'm multiplying that times a negative 48. And I'm dividing by x squared minus 16 to the 3rd power. Well, with all those minuses in there, I can distribute through that a minus sign and make everything positive. So I'm ready to go to my number line. If you don't mind, I'll put it up here. And I'm putting the second derivative on the number line. Still, where is this going to equal 0 or undefined? It's undefined again at -4 and 4. But they're asymptotes, so they're not going to be points of inflection. And you see the numerator, everything is positive. 3x squared plus 16 is never going to equal 0. So there are no other critical values. So if I go to since the numerator is always positive, if I pick a really big negative number and put it in here, I get positive. If I pick a number between -4 and 4, like 0, the denominator is going to be negative, because you have a negative number cubed, and to the right, it's positive. So that means that the function y is going to go concave up, concave down, concave up. And since these two things, even though the concavity changes at -4 and 4, those are asymptotes. So they basically is saying there are no points of inflection. But it's still, this is going to help us because it tells us the concavity. And we're almost ready to graph our sketch, but we still need a point to work from in each section. We've already got a point here, so what would be a good point to the left of -4 and to the right of 4? I'm going to pick 5 and -5. So if I put those in there, I get 50 minus 4, so 42 over 9. So a little bit bigger, or a little, somewhere between 4 and 5. So if I go to this point, I'm up here somewhere in the graph, and -5 would do the same thing on this side. And now I'm just ready to follow my number lines. I know that in this first section over here, I have to be increasing the whole time. And I have to be concave up. So I start at this horizontal asymptote and go increase and concave up until I get to this asymptote. In this next section, I go from increasing to decreasing, and at 0, I have a 0 slope. And I have to go concave down the whole way. So I'm going to start at this asymptote, go increasing and concave down to a 0 slope, and then decreasing and concave down. And then lastly, in this last section, I have to be concave up and decreasing this whole time. So I start at this asymptote, decrease and concave up to this asymptote. And we've got a graph. Now that did take quite a long time, but I think you can see by plugging values into here, there's no way that you would figure out what that graph looked like. So the derivatives really did help us. And sometimes you can even, when you get done, make a little picture out of it. You can put a little hat on the guy's head, and we have a little guy. Okay, so let's just try one more, but make one that won't take quite so much time. A little bit easier one. This is also a rational function right here. But this one, when I look for asymptotes, I'm not going to find any horizontal asymptotes. A vertical asymptote x equals 0 makes the denominator 0 and not the numerator. So x equal 0 is going to be a vertical asymptote. But when I take the limit of this as x approaches infinity, if you remember back when we did limits, when there was a higher power here than there was in the denominator, you're not going to get a horizontal asymptote. The end behavior you get by kind of ignoring this -1, and we end up with y equals 2x as our end behavior model. And you know, as x approaches infinity, that's going to go up to infinity. So it's going to go up like this, and as x approaches negative infinity, the function's going to go to negative infinity, so it's going to go down. And we even know how it's going to proceed up and down. It's going to proceed like y equals 2x. So I can actually just make that asymptote by making a slope of 2. So I have y equals 2x. And basically, they're asymptotes, so the function never quite touches it, but it looks so close to the function that we can actually sketch the function to look pretty much just like what the asymptote does at those ends. Well, let's deal with local maxes and mins and points of inflection and concavity, all that type of thing. I think you can do yourself a big favor here by simplifying this. 2x cubed over x squared is 2x, and then you have minus 1 over x squared is minus x to the -2. So if I rewrite it to be 2x minus x to the -2, when I take my derivative, I get 2 plus 2x to the -3, which for analysis purposes, I'm going to write 2 plus 2 over x cubed. And like usual, I set that equal to 0 or undefined. And in this case, you find out it's undefined at x equals 0. And is it ever equal to 0? Well, you can either go through some algebra or just kind of notice that if you put in -1 for x, you get 2 minus 2. So the critical values are going to be x equals 0 and -1. So if I were to put those on the number line, -1 and 0, but remember, 0 is an asymptote, so it can't be a local max or min. Now let's pick some values. Pick a big number, a big negative number. If I put a big negative number in here, I'm going to be positive. If I pick a really small negative number, that makes this really big negative. And then if I pick something positive, both of these are positive. So I see that my function does what? It goes up, and then it goes down, and then in this other section on the other side of the asymptote, it just goes up. So I can see at -1, I have a local maximum. -1 what? I put that in here, and I get -3 over 1, or -3. So that's a local max. At -1, -1, -3. And I have no local minimums. Now I can go to my second derivative. And I think the best place to take the second derivative is from here. So if we take our second derivative, we get 0 minus 6x to the negative 4. Or negative 6 over x to the 4th. Well, x to the 4th is always going to be positive, except at 0 where it's undefined, but we know we have an asymptote there. So I think you can see you don't even have to put this on the number line. That is always going to be negative. So I can say there's no points of inflection, and I can say the function is always concave down because the second derivative is always negative. So I'm just about ready to graph now. Except that I need a point in both sections on the graph. Well, I already have one on this side of the vertical asymptote, but I don't have one on that side. So I'm just going to plug in 1. When I plug in 1, I get, let's see, 2 minus 1 over 1. Let's see. No, I get 0. So I get 0. So I get, I get the point 1, 0. Now I'm ready to graph. Well, in this first section, I'm going increasing to decreasing, and I know that I'm always concave down. So I start at this asymptote, and I have a 0 derivative here, and I go concave down. And then on the other side, I think I really was at 1, 1, not at 0, 1. I think I was right the first time. And at this time, I start here and come down here and go down to this asymptote. So I think that is the graph. Sorry, we've got 2 points there. That was the easiest part of the whole thing. But when you plug in 1, you get 1 over 1, which is 1. So this point is not there. Anyway, that still would have been pretty hard to do just by plotting points. Okay, so let's just end this thing with one more max-min problems. These are so important, and this one is going to involve getting into a rational function. So say you're a packaging engineer, which is it is a type of engineer where a lot of people work at, and say you work for a large movie chain and they want to make, for the whole country, popcorn containers. So they're going to make 5 million of these that are going to hold 64 cubic inches of popcorn. And they want you to determine the dimensions of a cylindrical container because they want to put them into a cylindrical container. And they're not going to need a top on them because they're just going to sell them to you with popcorn in them and no top so you can reach into it. Well, we get to make the dimensions, and because there are 5 million of these containers, we want to minimize the cost of all this packaging material. So what we're going to do first is put in the dimensions. This is the radius and this is the height. And what we're trying to do is minimize the material. So it's the surface area. So we could call our function A, and it's a function of R and H. And there's no top, but we do have a bottom, so the area on the bottom is going to be pi r squared, and the area on the sides is going to be the circumference times the height. So that's the function. But as we ran into the other day, we have 2 independent variables and we have to get it down to 1. But we do know that the volume has to be 64 cubic inches. So the volume of a cylinder, we know, and we have to solve for something. Well, if I only had an r squared here and not an r, I would probably choose to solve for r, or r squared. But in this case, I have both of those. So I'm just going to choose to solve for h. And then I can go back and make this all in terms of r. It's pi r squared plus 2 pi r times 64 over pi r squared. And what do I know about my domain? R is a dimension, so it's got to be greater than 0, and I don't think there's any restriction on how big r could be. So the domain is really not that restrictive, just that r can't be 0 or negative. So if I rewrite this function, pi r squared plus, the pi's cancel, so you get 128, and then r divided by r squared is r to the negative first power. So it's a fairly simple rational function, but 128 over r is a rational function. So now when I go to take my derivative, I get 2 pi r minus 128 r to the negative 2, which I'm going to write 2 pi r minus 128 over r squared. And I want to set that equal to 0 or undefined. Well, it's only going to be undefined at r equals 0. But is this ever going to equal 0? Because r equals 0 is not in our domain. Well, if I want to set this equal to 0, I can basically just do that and cross multiply, and I get 2 pi r cubed equals 128, or r cubed equals 64 over pi. So r is going to be 4 over the cube root of pi. And we could now put that on the number line. But I'm deciding that we haven't really tested the second derivative test for local maxes or mins, and it might be a good thing to do that. So let's take the second derivative, which is going to be 2 pi plus 128 r to the negative 3. Well, 2 pi is always positive, and for positive values of r, which we have, this is always positive, so we can see that the second derivative is always greater than 0. The function is always concave up, which means if you have a 0 derivative and the function's concave up, that point has to be a minimum. So we don't even have to put this on the number line. That would have worked also if we used the first derivative test, but it's always good to check out the second derivative test. So we've got our answer. That is going to be the absolute minimum, where r equals that, and then h is going to be 64 over pi times r squared, which is 16 over pi to the 2/3. Well, 64 over 16 is 4, and pi over pi to the 2/3 is pi to the 1/3. So the interesting thing is, r and h turn out to be the exact same number. So we found out what the dimensions of that should be, and we see that basically you're going to make something where the radius is the same thing as the height, and your container is going to look something like that. And you're going to minimize the amount of material you use for those 5 million containers. So I hope that gets you one more time to see what derivatives can do to help us graph complicated functions and also to solve Maxmin problems. So have a good day, and I'll hopefully see you the next time.